All right, let's talk about the engine that powers so much of the AI we see today, the feed-forward neural network. We're going to break down how these things actually learn and how they go from drawing simple, straight lines to figuring out the incredibly complex patterns all around us. Let's get into it. You know, a lot of simple machine learning models work by just drawing a straight line. Think about it. Positive movie reviews on this side of the line, negative ones on the other. And that works great for really simple problems. But let's be honest, the real world is almost never that neat and tidy. So that brings us to the big question, right? What happens when your data isn't in two neat little clumps? What if it's all messy and scattered? How in the world does a machine learn to draw a complex, squiggly boundary to figure out what's what? Well, the answer is we have to move past classifiers that are stuck with straight lines, like logistic regression. We need something that can bend and curve. And that's exactly where feed-forward neural networks come into the picture. They're designed from the ground up to learn decision boundaries of, well, literally any shape you can imagine. And that's what makes them so incredibly powerful. Okay, so let's pop the hood and see what one of these networks is made of. And the good news is, if you get the basic idea of a single neuron, you're already most of the way there. We're just going to connect those building blocks together in a really clever way. So at its heart, a feed-forward neural network, or FFNN for short, is really just a classifier that's built with multiple layers of neurons. You can almost think of it as taking a simpler model, like logistic regression, and just supercharging it with the ability to learn those complicated nonlinear boundaries we were just talking about. A classic FFNN is pretty straightforward. It's got three main parts. First, the input layer, which just takes in all the raw data. Then you have one or more intermediate layers. We call these the hidden layers, and that's where all the heavy lifting and real processing happens. And finally, the output layer spits out the final answer. The key thing to remember is that information only flows forward, and every neuron in one layer is hooked up to every single neuron in the next one. It's this dense web of connections that's so important. Now, you might be thinking, hang on, if it's just a bunch of simple classifiers stacked together, what's the big deal? And that is an excellent question. It turns out there's a secret ingredient in here, one little trick that gives the whole network its incredible power. Because here's the catch. If all the neurons in your network are just doing simple linear math, then no matter how many layers you stack up, the entire network is still just one big, complicated linear classifier. You're still just drawing a straight line at the end of the day, which totally defeats the purpose. This is the absolute core of it. If you only use linear functions, stacking them up just gives you another straight line. It's like adding straight pieces of wood end to end. You just get a longer piece of wood. But if you introduce nonlinear functions, everything changes. Each neuron can now add a tiny bend or a curve to the process. And when you combine thousands of these tiny curves, the network can learn to draw a decision boundary of any shape it needs. So, the big takeaway here is this. It's not really the number of layers that's magic, it's the non-linearity that you bake into each neuron. That's the secret sauce. That's what allows a neural network to become what we call a universal function approximator, which is just a fancy way of saying it can learn to model pretty much any complex relationship you can throw at it. Okay, so the network has all this potential to learn these crazy complex shapes. But how does it actually do it? How does it figure out how to set up all its internal wiring? The best way to think about it is to imagine the network as a giant machine. I absolutely love this analogy. Just picture this huge, complex machine with maybe millions of tiny little knobs on it. Each one of those knobs is a parameter in the network, a weight or a bias. And the whole goal of training is just to figure out the perfect setting for every single one of those knobs so that you get the right answer out at the end. So, how do you know which way to turn the knobs? Well, the instruction manual for that is an amazing algorithm called backpropagation. After the network makes a guess, backpropagation comes in and calculates exactly how wrong that guess was. Then, it sends that error message all the way back through the network, telling each and every knob precisely how much to turn and in which direction to do a little bit better next time. So the whole learning process is this constant two-step dance. First, you have the forward pass, where data flows through the network and it makes a prediction. Then you have the backward pass, where the error from that guess flows back, telling every single one of those little knobs how to adjust itself. And the network just repeats this dance over and over and over, millions of times, getting a tiny bit smarter with every single pass. Now, here's where the story gets really fascinating. The core ideas we've been talking about, neural networks, backpropagation, they're not new. Not at all. In fact, they've been around for decades. So why does it feel like they've just taken over the world in the last 10 years or so? I mean, that's the million-dollar question, isn't it? If the blueprints for this stuff have existed since the 1980s or even earlier, what changed? Why do these old ideas suddenly explode and become so incredibly powerful right now? Well, the history is a story of ups and downs. The theory was there way back in the 60s, and people started applying it to neural nets in the 80s. But then progress just kind of stalled. For decades, we went through something called an AI winter, where neural networks fell out of fashion and other methods were considered way better. It wasn't until around the 2010s that a perfect storm of conditions came together and finally let these old ideas have their moment.
It really came down to 4 huge things hitting all at once. First, researchers found clever new tricks to make training really deep networks way more stable. Second, the internet gave us big data, just unimaginable amounts of information for these hungry networks to learn from. Third, we got the hardware. Powerful GPUs, originally made for video games, turned out to be perfect for the kind of math these networks need. And finally, all this success broke the AI winter, and a ton of new interest and money poured back into the field.
So the thing to realize is that today's AI boom wasn't just invented out of thin air. It's the result of decades-old theory finally meeting the modern technology, the massive data and the powerful hardware that I had been waiting for all along.
And all of this leaves us with one final and really important question. This incredible flexibility is a neural network's greatest strength, but it's also its greatest weakness. If a network can learn any pattern, what stops it from hallucinating? From perfectly memorizing all the random noise in its training data and then completely failing when it sees something new? This problem is called overfitting, and figuring out how to control for it, well, that's a whole other story. Thanks for joining me.